Now, this module is fairly short because, it is really an introduction today. We're not going into too much of depth. But what I'd like you to do, guys, is when you go back and do your reading, your studying, I know both of you, and maybe there are some others in this unit, I don't know, might have full-time jobs, quite busy, you've got families. So I do appreciate there are a lot of other challenging, other demands on your time. But my request is, like any subject that you study, whenever you begin to study, please put in your 100%, look into it, do a little more reading, and trouble me. I think you need to trouble me. You need to get your money's worth and time's worth, because I think that gives me joy as well. Because it's not that I know all the answers, definitely not. If I don't know, I'll definitely go and ask someone to get some answers. But do a little more reading. I think it will certainly help you. Obtain understanding, processing methods, symbols. I've already spoken briefly about that, alluded to that previously. Read and interpret PFDs, and use from PFDs for plant layout and piping design. Now, there are a number of processes. Now, these are different examples. But effectively in life, there are, in chemical engineering problem situations, there are two key processes. One is when there's a physical change. A physical change is generally reversible. So I can heat something, it evaporates. I can cool something, it condenses. I can dry something, I can wet it. So all these are in some sense reversible processes. So these, where there's a physical change, is known as a unit operation. And it's very nicely summarized in the sentence at the bottom, are used primarily in the separation and product purification steps. Very clear. Now, a unit process, on the other hand, we are processing. In other words, there's some breaking down, there's some synthesis, there's some addition. So we're doing something to the chemical. We're not comfortable having just the chemical by itself. We want to do something. We really want to we are bugging it and want to do something to it. So alkylation, where we add an alkyl radical, for example, methyl radical. Hydrogenation, we add hydrogen to break the bonds. Very commonly used in, well, we've got petrochemical, but also used in edible oil. Thermal cracking, fluid catalytic cracking unit, FCCU, certainly used in oil and gas quite a bit. Polymerization, what would we do without polymers? Where you're adding a repeating molecule like CH2 would be added a number of times to get PVC. Oh, sorry, yeah, PVC. What is CH2? Yeah, I forget what it is. Sorry, it will come back to me shortly. Chlorination, where we add a chlorine, bromination, a bromine, and so on and so forth. So unit processes primarily occur in chemical reactors, change of chemical compositions, feed, raw materials. Now, what we have here is a starting point of a PFD. So I won't even call this a PFD. This is more like just well, it's got a process flow diagram. You can call it a process schematic, if you wish, a process schema. But in the fluid catalytic cracking, what it's showing you, and this is something you'll be quite happy to put in a concept study, or a study that you're doing for someone where the amount of design that's going into the process is not more than about 5% design. So you've shown the main pieces of equipment. One is the regenerator for the catalyst. Then you've got your reactor separation vessel, where it strips out, and you've got your fractionator, which is nothing but a distillation column, and you've got your slurry or settler. That's about it that you have to worry about. But what is important in this sort of diagram, I mean, while we are talking about fluidized or fluid catalytic cracking, what it is trying to show you is that you've got your raw oil coming in here. What happens to this raw oil? This is your crude oil. You're now trying to break it out and provide and get a variety of cuts. So by cracking it, so what is cracking? What do we mean by cracking? Sometimes I have these very long chain hydrocarbons. When I have long chain hydrocarbons, it's not going to burn well as a fuel in a car engine or an automobile engine. I need it to be shorter chain. I need some rings in it. And that is where you're trying to provide break some of these bonds. So you provide some rings, shorter chains, and we end up, when we fractionate it, in your C4 lighter, that is butane and lighter, which normally becomes your LPG. You've got gases. So LPG is normally propane, butane primarily. So you do have a demethanizer and the deethanizer. The methane, these are good products. The LPG is a very important commercial product which you can then sell in the domestic market, a lot of money. Gasoline is the petrol you put into your car. Light gas oil, generally light gas oil to heavy gas oil, that range is your diesel mix, depending on the type of fuel that's going in. Heavy gas oil can be used for some of these gensets, generators. As you go heavier in the gas oil range, somewhere when you come out here, you get your real crap stuff, real thick rubbish, which can be called bunker oil. So you use a bit of gas oil and mix it with bunker oil and reduce the reduce the viscosity, so you can pump it, and it is generally burnt quite happily in ships. But what the key processes that we have here is the regenerator for the catalyst. We've got a separation vessel because you want to recover the catalyst. You have a fractionator, which is a distillation column, which breaks up the product. And we've got a slurry settler because what happens is the bottom oil that remains uncracked goes through a slurry settler where you get rid of all the rubbish, and then the oil is sent back and recirculated. So you don't want to waste anything. The alkylation process, very much similar, low molecular weight propylene and butylene with isobutane. These are the key. The octane number of the alkylate depends mainly on the kind of olefins used and upon the operating conditions. So very similar. You've got propylene and butylene. So your C3 and C4s are coming in. And isobutane, present catalyst, whatever it is. Hydrofuric acid is a very nasty acid. What we are interested here is we've got this big reactor sitting here. That is a key part of this process. We have fresh acid coming in. So the reject acid has to go out. Your feedstock comes in. Whatever comes out goes to the acid settler. You have physical separation there. Caustic scrubber, you get rid of any of the acids. Then you got a de-isobutanizer. You get rid of the isobutane. And what remains is your alkyl radicals. I mean your alkylate. Your alkylate, as they say, while you use propylene and butylene, it's really adding the alkyl radical. The alkyl radical could be methyl, ethyl, propyl, or butyl radicals. So so they have found that these radicals, when you add these radicals to this, you end up, or these groups would be a better term, you add these groups to the gasoline, you end up with very good antiknock properties. So, I think this is an interesting picture, more from an interesting graphic from understanding what happens to crude typically. So, normally crude oil, right at the top, you get your, at this point, normally you get your gases that come out, your fuel gases, and less than most of your methane, ethane, propane, all that comes out there. Alkylation of the slightly heavier, treated blending, you get very high octane gas. Useful. What comes out here at this position? Your gasoline comes out, which is, now you don't get jet fuel. Jet fuel is generally about 140 degrees. Your gasoline is about 90 degrees. Jet fuel is a bit lower than that. You have, at this stage, you might end up with slightly heavier naphtha. This could be light naphtha, heavy naphtha coming out here. Heavy naphtha gets reformed, and that gives you kero and jet fuel, diesel and heating oil. You go further down, and as you go lower and lower, you end up with heavies. So what comes out at the bottom is your asphalt, also known as bitumen. And this asphalt is then sold for a number of, well, all our roads and so on and so forth. Now, what are the key principles? Now, why is a process engineer important? Because one of the key things that we do is provide the mass and energy balances. Once we do the mass and energy balance, we have everything provided. So that is always a challenge. We need to understand fluid mechanics. Why? Because we need to determine the pressure drops. Understanding the concept of pressure drops will allow us to determine the pipe size. What about the heat transfer? We need to understand heat transfer because we size heat exchangers. How big should my exchanger be? What sort of capacity should my heat exchanger have? These are questions we ask because we are able to size heat exchangers. Chemical reaction engineering. We need to be able to design a reactor, understand the reaction order. Do we have a first order reaction, second order reaction? How can I make my reaction go faster? How do I control my rate of reaction? Do I need a catalyst? Mass transfer. This is critical. All the unit operations we spoke about come under the class of mass transfer. Distillation, extraction, solvent extraction, drying, evaporation, particularly important cooling towers. So all this comes under mass transfer. We need to understand a little bit of process control because, as I said right at the start, we need to monitor. I need to be able to maintain my process parameter at the desired level. I also need to understand my process engineering economics. So it is actually quite complex. There's a book in process engineering economics called, which if you have got access to a library, let me just type it out. Come on. What is this? Sorry, it's not, maybe I'll just type it here. The book, the author's name are Peters and Timmerhouse. So if you can get an idea, get access to Peters and Timmerhouse from your library, it's just worth reading. It gives you an idea of what is involved in this thing. I want to type it. Oh, it does. Good. Let me put that. Peters and Timmerhouse. I think plant process economics, I think it is certainly worth looking at that book.